much easy to understand because you have px1, py1, pz1. Right? So ground state is very easy to understand. But you can make excited states, everything is spherical. That's the important point, it's not just ground state. So if you want to make the atomic charge density as spherical, you have to give a potential. The atomic Hamiltonian by itself will always lead to a spherical charge density. So of course, if you give an electric field, magnetic field, that's a different point. Then lots of interesting physics will take place. But as far as the electronic structure of the atom themselves, they will always remain spherical. Of course, each of them has all details. I'm not going into this. There are nodes. If you look at the 1s orbital, there is no node, 2s orbital, 1 node. These are called radial nodes, then there are angular nodes, and so on, which are interesting, but at this point, it really doesn't add value to what I'm trying to say. So I just want to go to this energy level. So for example, let's see. So for example, this is the hydrogen atom. This is what I wanted to say. So you have y equal to 1. For hydrogen atom, you have these boxes, 2s and 2p, but they're equal energy. So 3s, 3p, 3d are equal energy. So for all one electron, which is hydrogen atom, or any hydrogen-like atom, of course when I'm saying hydrogen atom, it could be helium plus. Because helium plus is like a hydrogen atom. So as long as they are in a central potential, that is important. One electron in a central potential. So helium plus, Li2 plus, and so on, they will have the same structure. So I must define that whenever I'm talking of hydrogen, I'm saying it's a hydrogen-like atom. So orbitals on the same level always have the same energy. So because of the degeneracy that you have between these, and so that's the reason it only depends on principal quantum number. And that is where Bohr was right. If you look at that, Bohr was somehow right. It's an accidentally right, but it was right. So that's the reason for one electron atom, you don't need to do anything more than Bohr if you're interested in just the energy. And that is what we are principally interested in.
So, just
yes.
So this is all true when you don't input the spin. The moment you input the spin, it will go.
How? One electron atom, it doesn't matter. One electron atom, it doesn't matter. Up spin, down spin, degenerate. For a single electron, if the spin is, the discussion of spin is actually trivial. The spin comes in for 2 electrons. Yes.
Unless you apply an external magnetic field.
Yeah, as long as it's an isolated thing, it doesn't matter. You either do up spin, down spin, it has no meaning. Alright. So, however, as soon as we go to other atoms, the number of electrons increases, then you have the separation. And that is the reason I said energy depends on N and L. But now the energy actually depends on S and P. So the 2s has a lower energy than the 2p, 3s has a lower energy than 3p. Interestingly, then 4s comes, and then 3d. So this is more difficult to understand, the S and D, and then of course, then 3d, 4p, etc. So this is basically, and you fill up the electrons using what is called the Aufbau principle. So depending on the number of electrons, you keep on filling as far as general atom in the order of increasing energy. So you have to fill a subcell, then go to the next subcell, and so on. And that is how the electronic structure of the atoms are eventually written. Again, please remember, this is on the assumption that the entire atom's description is on a single determinant. In fact, I'm going to say a little bit more later when I bring in the electron correlation that this is an approximate definition. So for example, when I said boron atom, 1s2, 2s2, 2p1, it's actually an approximate wave function for the boron atom. Right? Because it has 5 electrons, I will show that such a simple description cannot be an exact wave function for a 5 electron. So exact wave function has to go beyond this. But assuming that I have the dominant configuration, and that is what the chemistry and the physics people actually write, is what they write for an atomic electronic structure, remember, is the dominant configuration. This is important because later in my talk, one of the days, I'm going to move to the electron correlation. So that is why there should not be any confusion. There is still a dominant configuration, which is very often called the Hartree fork. In fact, we will talk about that. The Hartree and fork actually told how do you get these functions, these orbitals. For hydrogenic orbital, it is very easy because you simply solve the Hamiltonian. That is solvable. What do you do for many electron atom? That's a very fundamental question. What is 1s orbital for helium? Or 2s, can I use the hydrogenic wave function? No. The form will be different, although the degeneracy will be there. So what exactly should be the form, what should be the parameter in the exponential, etc., etc. All that can be explained by Hartree form, and this is essentially in the solid, which is equivalent to band structure or band theory. So Hartree and Fogg did a very nice thing for atoms, and we can define our 1s, 2s, and 2p for each atom. So for each atom, my 1s will be different. Not only energy will be different, the functions will be also different for each atom. And this is how we actually describe a dominant structure, which is called the Hartree-Fogg determinant. So very often when we write electronic structure, we actually ignore other configurations. We only write the dominant configuration, which is essentially can be called today Hartree-Fogg configuration.
So what is a simple way to understand why the 2s, 2p degeneracy is lifted? That's okay.
Well, the simple way is because of the fact that the angular momentum is higher for the p. So that actually leads to, so when you say energy of an electron in 2p, okay, in a multi-electron atom, what do you exactly mean? For a multi-electron atom, we have only levels.
Looking at transition between.
Yeah, we have levels. So you want to call this 2s and 2p only because of the angular momentum, the L values. But what you are essentially asking is that how do I get lots of energy levels. So you have to look at, for a multi-electron atom, as a wave function, which is a determinant of composed of many orbitals, right? I have many orbitals. I now get the orbitals. I order the orbitals in order of energy, increasing energy, and then look at their L values. And then I find that the higher L values within a quantum number is usually higher, but not always. As you can see here, the 4s is actually lower than the 3d. So it's not always true. It's true up to a point, no doubt. So this is a more subtle effect, and there are lots of discrepancies depending on the atom. So it is indeed a matter of details in terms of actual calculation when you do the Hartree-Fogg calculation. But in general, we find that for all atoms up to 2p, 3s, 3p, this is always kind of followed.
In terms of electron-electron interaction.
Yeah, these are all electron-electron interactions, of course. So basically the SP is electron-electron interaction. But electron-electron interaction, average for a single determinant. You are still calling a single determinant. So the genuine electron-electron interaction, there is another part which we will describe later as electron correlation, which will come later. Alright, so somebody mentioned spin. So of course there is a spin of the electron, there is an up spin and a down spin, and we have two values, plus half and minus half. And so you have an orbital diagram where this ms equal to plus half and ms equal to minus half is important. This is particularly important when now I have two electrons, and I am going to explain that in the blackboard. What happens when I have two electrons? Now the spins become very, very important. And this actually has a very important idea of Pauli exclusion principle, that how do I put the electrons in an atom. And the very important idea is that no two electrons can have same 4 quantum number. Now 3 I've already said NLN, and 2 more comes with this spin quantum number, which are either plus half and minus half. But the important idea is that no two electrons in a one atom can have same 4 quantum numbers. So this is very important in Fermi orbital. Of course, this is trivial. If S subcell field 2 electrons, P can have 6, B can have 10, F can have 14, and so on. And then we have a Ohm's rule, that if I have the lowest energy arrangement of electron in a subcell is obtained by putting electrons into separate orbitals at the subcell with same spin before pairing the electrons. So that's why this is very important, the spin. And I'm going to come back and prove this in the blackboard. If not today, in the next class, depending on my time. So I'm just going through my slides to get you review. The Ohm's rule actually is something that I'll prove. Now, although Ohm's rule is taken as a rule, Pauli principle can also be proved for quantum state, that I will do that. And with this, if you calculate the lowest energy state is for ground state, any other allowed configuration represents an excited state. How do I pair up the ground state? This is called the building up of the Aufbau principle. It actually successively fills the subcell with electrons in a specific order. So the order is something like this: 1s, 2s, 2p, 3s, 3p, 4s. So this is actually nicely done by this. So this is how the order is filled in general. So you can see that we don't fill 1s, 2s, 2p is okay. We don't go 3s, 3p, and 3d. So you go 1s, 2s, 2p, 3s. After you fill up 2p, you go to 3s. Then 3p, then 4s. So So that's how this arrow means. You don't go to 3D, then start from 3D, 4p, 5s, then go to 4D. So this is what actually a very interesting principle, because this is how the ordering of energy levels come. This is of course something that I am not devising. The ordering has to be according to the increasing order of energy, the filling up. Okay? So this is how the changes take place. So usually you have 2p, 3s, then there is 3p, and then there is 4s, not 3d. So that is the reason you don't fill up 3d there, you go to 4s. So this is very interesting form in the Hobsbawm principle, and you can see that there is a nice arrangement if you go like this diagonally. So it's very easy to remember also. If you write the all the different orbitals, it's very easy to write and fill up the atomic shell. So it results in the following order: 1s, 2s, 2p, 3s, 3p, then 4s, then 3d, then 4p, 5s, 4d, 5p, and so on. So you can actually find this order exactly from here. And all atomic electronic structure actually obeys this. So you can then define, and the chemists are very important, this S block element, P block, D block, F block element, depending on where the valence cells are. There are a few exceptions. This is something that is good to remember. The exceptions are much more difficult to explain because of the multi-electron interaction. There is a change in certain cases. So that is why I said it is a matter of detail sometimes. For example, chromium and copper have been found by experiment to have the following downstate configuration. So you can see that the 4s comes later than the 3d. And what is more important, it is not 3d6, 3d5, then 4s1. And here also same thing, 4s does not come first. First 3d gets completely filled, then 4s. It is not 4s2, 3d9. So I think these are matter of minor exceptions. This cannot be so easily explained simply because this comes from the details of the calculation. When you actually solve the Hartree-Fock equation as an example of the Schrodinger, as an approximation of the Schrodinger equation. So these are some of the, like for example, bromine is a complete subcell, 4p5, so it's called P functions and so on. So very often we write, again, electronic structure, just for the students I want to write, say that we don't want to write such a big thing. So what we do, you identify the nearest inner shell configuration. So you write this as argon, which is up to 3d10, then 4s square, 4p5. So I can actually write this as this inert gas configuration, multiplied, and then 4s square, 4p5. So this becomes what is now called the valence cell. So it's very important to understand the core and the valence. So the inert, up to the inert point, it's a core. So if I like nitrogen, for example, it has a 1s2, 2s2, 2p3. So 1s2 becomes a core, and the 2s2, 2p3 becomes valence. So this is again a nomenclature that the inert part does not take place in the binding later. So I can more or less ignore and just concentrate on the valence electrons to describe much of the work. So that's the reason nitrogen is just called 2s2, 2p3. But note that between 2s2 and 2p3 you can't distinguish because the energy levels are not so different. So you can't call nitrogen atom valence is just 2p3. That would be wrong. So the distinction comes more or less after an inert cell has been formed, what else is left. So the nearest inert cell of nitrogen is actually helium, 1s square, and then you do. So here, for example, the nearest is 3d10, and you only consider bromine as 4s2, 4p5. So very often they will say s2p5. In fact, there are jargons that you just call this is s2p5. But you have to understand, it doesn't mean that only 7 electrons. The core has actually been eliminated. The reason I'm saying that many of these will be actually used later, particularly for the higher atoms and so on. So I think it's important to understand the jargons. So we call boron atom just 4s2, 4p5 eventually. Which means, of course, there is a noble gas or the pseudo-noble gas core, which I'm not writing because it just becomes too large. So this is a simplification that is usually done. For main group elements, again, inorganic chemists actually do a lot here, an S or P subcell is being filled, basically. For a D block transition element, it means D subcell is being filled. For F block transition element, F subcell is filled. So when you say main group, D block, F block, they have a specific meaning. That the electrons have gone into that subcell, D, F, or just S and P. So that's the main group. So you will hear from inorganic chemistry people that, oh, he is working on main group chemistry. So you have to understand, sometimes the jargons are very difficult to understand. So that is the reason I'm saying the main group chemistry essentially means they are looking at S and P subcell. When you say D block transition, that means they're looking at a D subcell. At least some electrons are there in D subcell. And similarly here, the F subcell is there. We also talked about the magnetic properties. Of course, if you give a electron behaves like a tiny magnet, and the electrons which are opposite in spin cancel with each other. Again, this is not important for a one electron atom, but for others, we can actually start to classify atoms based on their behavior in a magnetic field. So if I have a weakly attracted by magnetic field, usually this is due to the unpaired electron, this is called paramagnetic, and if you have only paired electron, this is called a diamagnetic substance. So this is how the magnetism comes in. I think I will close my general talk here. I just wanted to bring in with some of the nomenclature. Do I have time now? 15 explain to you that we are interested in stationary states of energy, you get NLM quantum number. The problem starts when you have more than one electron. And this is the fascinating thing. First of all, the spins come in. So how do I spin pair and so on. So there, the first important thing is the Pauli exclusion principle, which is often called the statistics which comes out of Fermi-Dirac. So I just want to explain what happens for many electron problems. So in general, this is a quantum particles, not just many electrons, but it can be a quantum particles. So one of the important part in the quantum particle is that they are completely indistinguishable. So when I say quantum particle, essentially it means they are completely indistinguishable. So I'm going to show this for a two-particle Hamiltonian. It essentially means that if I write the Hamiltonian of the two particles, it has the kinetic energy of the electron or particle 1, particle 2, and the potential energy. But what is important, that since they are completely indistinguishable, I can write this Hamiltonian also as 2 and 1. So I can interchange the coordinate of 1 with the 2, and I get the same Hamiltonian. So this is a very interesting part of this Hamiltonian. So this is actually true for all quantum particles, including electrons. Let me now define an operator which is called the permutation operator, P12. So this is called the permutation operator, and I will define what is this permutation operator does. So the job of this permutation operator is to allow, if it acts on any function, not just the eigenfunction of the Hamiltonian, any function, it simply interchanges the coordinates of 1 and 2. So I think it's very simple to understand. I define an operator, which is a permutation operator, and I allow this to act on an arbitrary function, phi of 1, 2. What does it do? It simply makes phi of 2, 1. So that's the definition. Now I contain that my quantum Hamiltonian, H of 1, 2, and this permutation operator P of 1, 2, if I multiply in this manner and the reverse manner, they are identical. So I'm going to prove this. It's a very simple proof. So essentially I'm saying that the Hamiltonian commutes with the permutation operator, my quantum Hamiltonian. So how do I go?